Hi there, folks. Today we're looking at fitting lines to data. And the first thing we need to do is determine if there's some kind of pattern in terms of the data we're looking at, all right? And we call that correlation, all right? So correlation is if there's a pattern exists, if there's a relationship between the two things, all right? That's this whole idea of correlation, all right? For lines, for our purposes, we're only looking for the pattern that kind of represents a line. And so when you look at this, they're not perfectly lined up, but we have positive, negative, and no correlation. Positive correlation means the thing kind of looks like a line. And granted, if I draw a line through here, it's not going to touch all the points. They're all not all lined up. But if I were to draw a line right down the middle of this, the question really is, is that line a good estimate of those points? All right. And when you see all the points are kind of hovering around that line, so that line would be a good estimate or a good approximation of those values. So we say that the data kind of looks like a line. All right. So it's estimation. It doesn't have to be exact. It has to be close. Yeah, it looks like it's all kind of piled around that line. So we call that positive correlation because it represents a line with a positive slope. All right. And the idea there is that one value is going up as the other value is going up. There's a positive correlation. They're going up together. Okay. Negative correlation, likewise, if I look at this thing, yeah, it's not an exact line, but it kind of looks like a line. If I were to draw a line right down through the middle, does that line give us a good estimate of those points? And the answer is yes. All the points are kind of hovering around that line. So that line would be a good estimate of the points. And notice that line has a negative slope, so we call it negative correlation. In other words, as one value goes up, as the x values increase, the y values are going down. So like the relationship between those two values is kind of reversed. As one goes up, the other one goes down. We call it a negative correlation. And then no correlation just means that there's not really a pattern here. All right. If I were to try to draw a line and ask myself, hey, is that line a good estimate of those points? Well, not really. They're kind of all over the place. It's like if I were to draw this line. Is that line a good estimate of the points? Well, it's about as good as the other one, but still not very good. Is this line a good estimate of the points? Well, no, not really, but it's about as good as the other one. See, there's no line that kind of gives me a good estimate of the points. So we say there's no correlation here. And the idea behind correlation is if there's correlation and it looks like kind of a line, I can write an equation of that line, okay? And so that's what we want to do. We want to write the equation of that line if the correlation exists, okay? If there's no correlation, I simply can't do the thing, okay? So if a positive or negative correlation exists, the data can be modeled by an equation. And so here's what we do. We draw a scatter plot, which is essentially us just plotting the points. We take whatever data values are given and we just plot them. That's what a scatter plot is, okay? And that'll tell us if this thing has positive or negative correlation, okay? Or if there's no correlation. If there's positive or negative correlation, now we can draw a line, all right? And typically when we draw the line, we'll use 2 points. They can be any 2 points. Here it says 2 data points, all right? It doesn't have to be data points. Some students just really like to use data points. I prefer to use any 2 points because I can make it easier for myself, okay? The data points are nice because we can literally see them and we know exactly what those points are. But any 2 points will work as long as it looks like a line that looks pretty good, all right? So then we're going to write the equation of the line just like we've been practicing, all right? We'll put the thing in point slope form, and then we'll rewrite it in slope intercept form, something like that, okay? And then what we'll do is we'll kind of use that equation. The whole point of the equation is if the equation is a good estimate of the data, we can use that equation to plug in more values and get predictions using the equation, okay? For example, if I look at something like this guy, we've got the year and the number of smartphones. And a little disclaimer here, we want to make things easier for ourselves. When we're dealing with years, years are the worst because they're big, giant numbers, 1,990. All right. If we're not thinking of it as a year, that's an obnoxious number that we don't want to deal with. Here's the first thing I always do if we're dealing with years is I rescale it. I'll call this year 0. So then 1995 would be year 5. See, that's 5 years later. This would be year 10, 20, 25. Sorry, I skipped 15. Counting is pretty hard. Let me try again. 15, 20, 25, and 30. And that's the one we're going to make a prediction about, the year 2020. Okay? And here's the thing. If you want to call 1990 year zero and 1995 1 year later and go by increments, that's okay. All right? Your equation will look totally different from mine, but your prediction will be almost identical. Okay? I like to do it with that's year zero. And if that was 1991, I'd probably call it year one. Just to make things easier for myself, all right? But scale it down, all right? Rewrite those years as smaller numbers. So now basically here's my ordered pairs, ready? That first one is the ordered pair 0, 0. This is the ordered pair 5, 1, 1047, 15, 121. But see, these are much better numbers to deal with rather than having like 2010, 187. Ooh, that'd be rough. Again, it's not difficult to rescale it. Makes life a lot easier for you, okay? And when we look at this thing, essentially what I've done is basically made this my x and this my y. So now I have to go down here and I have to scale this thing, okay? And the idea here is I want to use as much of the graph as possible. So like down here, maybe I'll go, I'll just call this year 5, 10, 15. I'm just labeling every other, 20, 25, 30, and that uses a decent amount of the graph, okay? The y values might be a little trickier. They go from 0 to 244. A nice trick with this is just count how many spots you have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then what I do is I take something like 244, and I divide it by 10, which gives me like 24.4. Well, 24.4, I don't want to use that as a scale. Always just round up to something that's easy to use, like 25, okay? Or you could round up to 30 would be okay. So I'm going to count each of these little marks as 25, but I'm only going to label every other, partly because I'm lazy, all right? And partly because my handwriting is going to get really messy if these things start running together, all right? So I'm just labeling every other and 250. But see, the marks in between those are 25. And I'll just plot these, all right? So really, it's just a matter of, hey, let's treat that data like an XY chart. And now let's plot these things. So we got 0, 0. We've got 5, 1. And again, I'm estimating 1 would be down there somewhere. 1047 would be just under the 50. 15, 121. So right here is 125, so a little bit under that. 20, 187. That would be somewhere right in between there. 25, 244. Be just under this guy. Yeah, so that looks good, okay? And when we look at this thing, we just have to ask ourselves, does that have correlation? Does it look like I could draw a line that would estimate this data pretty well, okay? And the answer is yes, it looks like it's following a line, except for that first guy, right? This guy's kind of like an oddball, that 0, 0. And the reason that's an oddball is because smartphones weren't invented until 1995, which means this is kind of a bogus data value right here, all right? So I'd try to probably ignore that one. And so the idea here is we just draw a line. Let me get my line tool out. And just draw a line. I could say, hey, if I connected those first 2 points, would that be a good estimate of the data values? And it's like, well, maybe, kind of okay, but wouldn't it be better if I did something more like this, all right? And notice I could choose 2 of the data points and say I'm using that last data point and the first data point. But you don't have to use the data values. I would just draw a line that looks really nice, and then I would look for points that this thing goes through. Like right here, I could say, oh, it goes through this point right here, and it looks like it goes through this point right here, okay? And really, if you want to adjust the line to make it look really nice, because those points are kind of close together, maybe you want to adjust the line and say, you know what, I'm going to make it go through this point right here in the middle, and this point right here towards the end. I don't know if you can see which 2 I picked, but I made it go through this point, and I made it go through this point, okay? And see, by doing that, I get nice, neat values that I could write down and I could graph. And so here's the thing. If you choose any one of these points, all right, you're going to get a pretty good estimate. The ones that I just did in purple, let's see, that's the ordered pair. Oh, of course, I picked one that's a decimal. That's okay. That's 7.5. It's because it's halfway in between the 5 and the 10, comma 25. And this one up here looks like 22.5, comma, where am I, 200. Well, now I could find the slope. Ready? Let's find the slope of this thing. And you don't have to choose the same points as me once again. So let's see, the second y value minus the first y value, which is 25, over the second x value minus the minus, I'm having some trouble today. Okay, so let's see, that's a 175. Oh, my handwriting is getting really atrocious here. That's a fun word. 7, 5. All right. And then, of course, this guy, that's a 15. And now, I'm not going to leave that as a fraction. All right. I'm going to divide that on my calculator. Even if it comes out as a decimal, that's okay. So this came out to 11.67. And I just rounded it off. The idea here is we don't want to waste our time doing fractions, all right? We've been doing pretty much fractions for slope this whole time. But in the real world, guess what? Fractions are a waste, okay? So now I can write the equation. It's y, let's see, minus 200. I just chose the second point, equals 11.67. And then x minus 22.5. And now once again, I want to rewrite this in slope-intercept form instead. So I'm going to distribute. And yeah, I'm going to need my calculator's help to do this, and that's okay. Normally, when I do this in a class full of students, I have everybody pick their own points. And so what I do is I write everybody's equations up here. And what happens is I have like 5 different equations written. Sorry, I got to take a break to go plug this into my calculator, times 22.5. So let's see, I got a 262.575. So what I normally do is I have basically like 5 different equations written up here. And guess what? They're all correct. All right. There's not one equation that is better than the other. It's really kind of how well did you estimate this thing. Okay. Now I add that 200 to each side. So I end up with, let's see, y equals, sorry, my computer's being a little slow, having a little trouble, so I'm writing nice and slow. And looks like a negative 62.575. And this would be a perfectly acceptable equation for this thing. And again, it's an estimate. If you had an equation that said something like y equals 11.5x minus, 62, that would be fine as well, all right? And that would be just as accurate as the one that I have here, all right? It just meant that you chose 2 different points than I did. And you know what? Yours might be a little bit better than mine, okay? I could have drawn a line that maybe was a little bit more accurate in terms of how close it was to those points, all right? It's about drawing a line that looks good and then coming up with the equation of that line, all right? It's a little bit subjective in terms of coming up with that line, but then we just write the equation. So all of our equations might look a little different, all right? But they're all going to yield a similar result. Right here, I want to make a prediction. I want to know what's going to happen in year 30, which is 2020. See, now this is what I use that equation for. I can plug a 30 in here, okay? I can plug a 30 into this guy, and it'll give me an approximation of this thing. And once again, this is a job for my calculator. Everything you do in this part, the calculator is going to help you out with. So let's see, 11.67 times 30, and then minus the 62.575, and it gives me about 287.5. I'm just going to round it off. 287.5. And when you think about it, go back up here and think about that 287.5. Does that seem to fit with what's happening with the rest of the data? And the answer is yes. Okay, it looks pretty good in terms of the increases. Things are going up by about, 40 to 50 each time. And from 244 to 280, 287? Yeah, that's about 40 or 50 each time. Okay. And so just think about it in the context. And really, if I'd graphed this thing, I could have just estimated the slope by doing rise over run. You just have to be careful because each of these blocks is 25 going up and each of them is 2.5 going left and right. Okay. So you just have to be really careful with that if you try to do rise over run. Also, if you on the graph, you have the y-intercept, you could use that. You could just estimate the y-intercept by looking at the graph, okay? So again, these are estimations. We want to be close, okay? Here's another example. And again, this time, that's the value I'm going to predict is the 20. And so I have each of these kind of as an ordered pair here. It's the number of dragons and the number of unicorns. As the dragons go up, the unicorns go down because obviously the dragon is a natural predator of the unicorn. Okay, so again, this is my x values and my y values. And I'm just going to kind of go through this. Let me label this guy. So let's see. This is 1, 2, that's 3, 5, 7, 9, 11. Okay, so I just went by ones. I labeled every other so that my handwriting didn't run into itself. I don't know why I did green that time. I just did. Going up and down, here's a neat trick. Instead of starting at 0, you can just put a little zigzag in here and start at something like 300. All right. The nice thing about doing that is that you don't have to count all those values starting at 0. That little zigzag means, hey, I skipped a couple, and that's fine. All right. We just want to get an idea of what these points look like when I graph them. All right. So now from 300 to 1300, it's about 1,000. So I'm probably going to have to go by maybe 100 or so here. So that would be 400, 500, 7, 9, 1100. And I almost came up a little short. I could just squeeze this one in here, 1300. Again, it's an estimate, all right? That maybe wasn't the best scale to use. I maybe could have done a little bit better, but it's an estimate. As long as we can kind of get it on the graph and have some idea where that point is, that's all that matters, okay? And so now I plot these points. 1, 13, 22 is right up here somewhere. 3, 1, that's going to be right around up here somewhere. 5, right around that 900 mark. 715, going to be just a little bit up from that. 9, 483, a little bit down from that guy. And 11, 301 is going to be right above that guy. Okay? And so once again, I look at it and say, hey, does this look like a line? The answer is yes. And so I draw a line that looks good. And see, this one's neat because this one, maybe let's try doing rise over run. So here we go. I've drawn this thing, and it looks like I could kind of count the slope here. And this is why this can be a little bit tricky. You just got to be a little bit careful. Looks like you got a point here, point here. Yeah, it looks like a pretty consistent slope. Okay, looks like down 2 over 2, down 2 over 2. But keep in mind that's down 2 blocks over 2 blocks. Okay, over on this side, each block isn't 2 units. It's 100 units. So down 2 is actually down 200. Okay. So when we do the slope, let's do rise over run. It's down 200. And then over, down here, 2 blocks is just 2 units because I'm going by ones. So you just have to be really careful there. So the slope here looks like a negative 100. And so last time I picked 2 points off the graph, we can do that here, write it in point slope form and then convert it. Or I can just do rise over run from the graph. We just have to be careful with the scale. And then right up here, I can even look at this guy. Ready? If I keep that slope going back to and then up to, that's up 200. And right here, so that's 1,300, 1,400. So that's a good estimate for the y-intercept. And that's why we looked at all these different methods for writing equations line, because it makes stuff like this easier. So we can just do an estimate. Okay? So now here's my estimated value. Ready? Y equals negative 100x plus 1,400. And so now I have an equation that represents x as the number of dragons as y as the number of unicorns. There it is. Okay? But again, it's an estimate. And your equation might look a little different than mine, but that's okay. The follow-up question to this, oh, sorry, I forgot to do the predicted value. At 20, let's see what would happen. So if I plug a 20 in here, sorry, it's jumping around. So if I made a predicted value, again, that's my equation, just plug the 20 in. And again, this is a job for your calculator. So we go ahead and plug that bad boy into the calculator. Negative 100 times the 20 is going to give me a negative 2,000 plus the 1,400 gives me a negative 600. Well, let's interpret that. Does that even make sense? Can I have negative 600 unicorns? And the answer is no. What that means is at some point unicorns went extinct. I ran out of unicorns because there were too many dragons. Okay? And yeah, this is a ridiculous example, but so then the follow-up question to that, okay, that was my predicted value, which still gives me information even though negative 600 does make sense. What's the approximate number of dragons that will cause the extinction of the unicorns, right? So again, here was my prediction equation. Well, we just have to think about what each of these things represents, right? Y is the number of unicorns. So this is the number of unicorns. And X is the number of dragons. So extinction of the unicorns would be a Y value of 0. So I plug a 0 in here. It's asking me for the X-intercept, okay? And so now I can solve this thing. But again, it's all about estimation here. We're estimating a line that looks good. We're estimating the equation of that line so that we can use that to estimate future values, okay? And now we divide each side by a negative 100, okay? And so the answer I get, 14. X equals 14. In other words, once I have 14 dragons, that's when the unicorns go extinct, okay? And so again, that's a silly example, but the idea here is we want to look at the data and say, hey, does it look like a line? Sure. Can I draw a line that looks like a good estimate? Yeah. What's the equation of that line so that I can make predictions about other values so that I can estimate certain things in the future, okay?